Hi, in this video, we want to take a look at continuous probability distributions. Now, we're going to be working through the PowerPoint slides from Essential Biostatistics by Rosner, which is a Cengage textbook. All right, so for continuous probability distributions, we're talking about random variables where the numbers are just along the real line. Like any number along some portion of the real line are possible for this. So some of the times when we're talking about continuous probability distributions, we're talking potentially about any number on the real line from negative infinity to positive infinity. Other times, we're going to be interested in 0 to positive infinity. So the positive real numbers. And then other times we're going to have maybe from like 0 to 1. Like there's going to be a boundary, like there's a lower bound and upper bound. Now, something that is important to kind of think about as we talk about these is that any number potentially in the range of values is up for grabs. So potentially we could have our random variable give us 0.111119236. It's super long decimal. When we talk about continuous probability distributions, any number with super long decimal is possible. Now, in real life, when we're doing statistics, we don't have that level of precision. And so we'll go ahead and just think of it as we're truncating it down to the appropriate level. All right, so the biggest, most important distribution in all of statistics is the normal or Gaussian bell curve distribution. All right. The reason why this is important is because it works out if I'm working with averages, almost always I'm going to end up getting a bell curve shaped distribution. It just works out that way. And this is a huge cornerstone in all of statistics. So how we use this a lot of times is if I can convert my problem, if I can rewrite the problem I'm working on into a problem with averages, then I know the probability distribution is going to be approximately bell-shaped. And so then I can use that understanding of the probability distribution of the situation to do estimation and hypothesis testing. So this is huge. This is important. This is by far the most important distribution in all of statistics. All right, so many random variables such as birth weights, blood pressure, and other things just tend to follow a bell-shaped curve and approximately a normal distribution. These variables that are not themselves normal oftentimes are close enough that we can go ahead and use the normal distribution to understand what's going on. And you'll notice in the slide, it says normal distribution when summed. What this is alluding to is that if it ends up in some way, some shape, some form, I can represent the variable of interest as the sum or average of other variables. Usually, it's going to be a bell curve shape, approximately. And if it's approximately is good enough, then I can go ahead and get an inference using the distribution. And the normal distribution is in absolutely every single statistics software package there is, and there's plenty of tables. Back in the day, during like the Apollo missions, during the Manhattan Project, they used tables to look up the probability distribution values. So, like back before there were calculators, people sat down, pencil and paper, figured out particular values of the normal distribution, and then people had to take their problem, convert it over to how the table could handle things, look up the value, convert back to their problem, and then they would go through and proceed. For us, we have the benefit of a computer, and boom, we're just going to tell R, SAS, Python, Excel to do the computation for us. We're not going to mess around with stuff like that. All right, so to develop an analog for a continuous random variable, to the concept of a probability mass function, we need to know which values are more probable than others and to what degree. Okay, so what we're going to do is that if I want to know the probability of seeing my random variable between 100 and 150, I'm going to go up here, and I'm going to like take the region underneath the curve from 100 to 150, and I'm going to shade that region. That area the area is equal to the probability that I see a number between 100 and 150. Now, the cumulative distribution function, what that's going to do is that will give me the probability of seeing the value or less. So the cumulative distribution function for 100 would be the probability of seeing 100 or less. The cumulative distribution value for 50 would be the probability of seeing 50 or less. Generally, a distinction is not made between the probability that x is strictly less than little x and x is less than or equal to x. When we're talking about continuous random variables, remember how I talked about that really, really, really minute long decimal point? So since we're dealing with such long decimals and our continuous approach along the number line, it ends up that mathematically these two probabilities are the same. Because of the fact there are so many numbers along the continuous real line, it ends up that the probability of any one particular value, and I mean exactly that super long decimal representation of that value, the probability of seeing exactly that is actually going to be 0, even though we have a total probability of 1. The expected value and variance for continuous random variables have the same meaning as they do for discrete random variables. Now, to compute them, it's a little bit more complicated. When I have discrete random variables, expected values and variances can be computed using sums, using addition and multiplication. When I talk about continuous random variables, we have to invoke some calculus. And since we have to invoke calculus, we're not going to do it in this class. And we're going to denote the expected value as E of x or mu. And this is the population average of the continuous random variable. The variance of a continuous random variable denoted by var of x is sigma squared. It is the average square distance of each value of the random variable from its expected value. And we're going to write this as, so I'm going to take a random variable minus expected value. I'm going to square the difference, and then I take the expected value. So here, it would be a little bit clearer if we put another parenthesis around this to make sure that the square is on the inside of the expectation. And we can re-express in short form as expected value of x squared minus mu squared. So this calculation will always be the same as this calculation. And so either one of these are equivalent. Usually when we're talking about it in like academic papers, we represent it in the first way. Now the standard deviation is just the square root of the variance. The normal distribution. All right, normal distribution is by far the most widely used continuous distribution. It is vital to statistics. It's frequently called the Gaussian distribution after the well-known mathematician Carl Friedrich Gauss. He is considered the last mathematician to be a master of all fields of mathematics. The field of mathematics has grown so much that we believe that it is not humanly possible to understand all fields at this time. The normal distribution is generally more convenient to work with than in any other distribution. So it comes up in so many places that we built tools for us to access it. So it's easy to get to, it's easy to understand. And a lot of the theoretical pencil and paper work is actually easier when we're working with the normal distribution than with other distributions. So, body weights approximately follow a normal distribution. Other distributions that are themselves not normal can be made approximately normal by transforming the data using different scales or logarithmic scales, square root scales, stuff like that. Usually, any random variable that can be expressed as a sum of many other random variables can be approximated by a normal distribution. Example, a physiologic measure are determined in part by a combination of several genetic and environmental risk factors. And so what's going on here, if we have multiple things coming in and influencing what's going on, it ends up that things tend to average out for most people. Now, there are a few people that genetics and environment make things go up, make them go down. And in that situation, we're going to get approximately a normal distribution. So whenever we have multiple variables feeding into and impacting the one of interest, we can usually use the normal distribution to model the one of interest. A lot of estimation procedures and hypothesis tests assume that the random variable being considered is under the hood a normal distribution. So here's the probability density function for the normal distribution. So you'll notice that there is that E exponential from college algebra, and we have an exponent up here. So it's x minus mu squared divided by 2 times the variance negative. And then we have this rescaling factor to make sure that everything adds up to 1. So mu can be any real number. Sigma has to be greater than 0. And this exp is E. It's approximately 2.17828. And the square brackets are in the exponents of E. The density function follows a bell-shaped curve with the mode at mu, and the most frequently occurring values are close to mu. The curve is symmetric also, and it has flexion points on either side, 1 standard deviation to the left and right. A point of inflection is a point at which the slope of the curve changes direction. The distance from mu to the point of inflection are an indication of the magnitude of sigma. Using calculus methods, it can be shown that mu and sigma squared are the expected value and variances, respectively, of the distribution. All right, so you'll notice that here, this is like a steeper slope, and here it is a less steep. Like if we were skiing, we know it's steep, and at this point it kind of starts flattening out. That's what that point of inflection is. Well, you'll notice that here mu is the peak of it. It's the top. It's where we see the most likely it's the most likely region of the number line, and a large portion of our data is going to be within. In fact, 68% of our data will be within 1 standard deviation of mu. A normal distribution with mean mu and variance sigma squared will generally be referred to as n mu sigma squared. The height of the normal curve is always 1 over the square root of 2 pi sigma. So what this visualization shows 2 different normal curves with the same variance but different mu. And so you can see that the area, or basically these are just shifts of each other. They just shifts of each other. These are 2 normal distributions with the same mu, the same expected value, but different variances. So here, the one that's taller we're going to see proportionally more stuff close to mu, while the one that's pushed down, we're going to see things farther out more frequently for this distribution. Now, the normal distribution with mean 0 and variance 1 is called standard normal. And we write this as N0, 1. And this is symmetric, just like a symmetric function in college algebra. 68% of the area under the curve is within 1 standard deviation of mu. About, I'm doing this, about 95% is between plus or minus 2. It's actually 1.96, plus or minus 1.96 is 95%. We usually just say 2 for eyeballing situations when we're doing statistics. So 95% of our data is going to, most of the time is going to land within 2 standard deviations of the population average. And then, 99% of the curve is between 2.6 standard deviations left and right. The cumulative distribution function for a standard normal is denoted by this psi of x. And so here, this function, if I plug in a value, I get back the probability of seeing a normal random variable less than or equal to that value. And when you see a tilde, that means is distributed as. So x tilde standard normal, this is saying that x is distributed as a standard normal random variable. Here is the probability density function, and here is the cumulative distribution function. What this curve does, if I pick a value, so let's say I pick 1/2. If I plug in 1/2, this height here gives me the probability of being less than or equal to 1/2. So all the values on this part of the real line from negative infinity to 0 to positive 1/2, what is the area under the curve to the left of 1/2? And that's what's represented on this curve. Now the area to the left goes to 0 as x gets smaller and smaller, and the area gets close to 1 as x gets larger and larger. So as my x value goes to the left, this curve is going to get closer and closer and closer to 0. As I go to the right of the x value, probabilities add up to 1. So this is going to go higher and higher and higher, and it's going to get closer and closer to 1. It's never going to actually reach 1. It never reaches 1. It never reaches 0, but it gets super, super close. All right, so the symmetric properties of the standard normal distribution. So if I look at the cumulative distribution function of negative x, this is equal to 1 minus the cumulative distribution of x. So we have this special property. Now, all these steps in the middle are just showing how we arrive at that. Back in the day when people had to use those tables, like during the Manhattan Project, during the Apollo missions, like in the movie Hidden Figures, they had to use properties like this property in particular to look up values so that the tables could be smaller, so that the tables of numbers that they had wouldn't be unwieldy, too much to work with. All right, so a normal range for a biological quantity is often defined as a range within x standard deviations of the mean of some specified value of x. So what this is saying is that a lot of times when, like you get your blood work at the doctor, the printout actually gives a range of values of what's considered normal. And one of the ways to establish those cutoffs for what's normal is to use the normal distribution and to figure out like how far out we want to go in terms of standard deviations. All right, so if you're using Excel, the norm dist function will provide the distribution for us, the cumulative distribution function. The percentiles of the normal distribution are referred to in statistical inference. So we have upper and lower fifth percentiles and things like that. So when I'm doing percentiles, what I'll do to denote that, I'll put it as a subscript on the variable label, just so that we know what's going on. All right, so the function z sub u is sometimes referred to as the inverse normal function. All right, so if I put in a value, I can get if I put in a value into the cumulative distribution function, I get back a probability. What we're talking about here is going in the other way. I have a probability. I want to know the value of the cumulative distribution function. Now, if you remember from your college algebra class, when I have a monotone function, this function is strictly increasing, and it passes the vertical line test, so it's a function. It passes the horizontal line test, so it's an invertible function. And so when I'm talking about that z of u, we're talking about the inverse of this function. Now, something that we can do is to reduce the amount of work at times. We can use that symmetric property to figure things out nicely for us. And that's what this part of the slide is talking about. So z of u, z sub u, is equal to negative z1 minus u. And so whichever one is easier to work with, that's the one I'm going to use. So conversion from a normal distribution to a standard normal. All right, so I'm working on a project, and I have normal distribution with population average mu and standard deviation sigma squared. One thing I'm going to do to make this easier to interpret, to look up things, to make figuring out what's going on easier, I'm going to go ahead, I'm going to take x minus mu, and I'm going to divide by sigma. This z is going to end up being normal distribution with population average 0, standard deviation 1, variance 1. This is standard normal. All right, so what I'm going to do to understand what's going on, when I convert over, I'm more familiar with this. I understand this much better. In the previous slides, I actually had, I had like the standard deviations were 1 on that slide. The reason when I was talking about the 68%, 95%, 99%, and so everything is in reference to that standard normal because I can convert back and forth using this formula. And here is a mathematical expression for getting the probability that a random variable is between two particular values. And you'll notice that here we're doing a conversion on the inside using this z formula. All right, so for any probability expression concerning normal random variables of the form probability of A less than X less than B, the population mean mu is subtracted from each boundary point, and then we divide by the standard deviation to obtain an equivalent probability expression for the standard normal. So what I'm going to do, I'm going to come up here, I'm going to subtract mu from all three of these, then I'm going to divide all three by sigma. This is mathematically correct. And so once I do that, this middle part will become z. Now here, I have a lower bound and I have an upper bound. This is standard normal. So what I'm going to work with, I'm not going to work with the actual normal random variable I want, I'm going to work with standard normal because that is referenced and understood very well. I'm going to figure out what I need, then I'm going to convert it back to the original distribution. So here's the original distribution. We can see that has an average of 80, and we can see that the standard deviation is bigger than 1. I'm just eyeballing that. And now over here, I take these values, I work out the details, and I see that this 90 corresponds to 0.83. This 100 corresponds to 1.67. When I convert to standard normal, I use the standard normal tools that I have to find out what is this area, and that tells me the area over here. Now, most of the time, you don't really, most of the time we can actually have the machine do the work for us. So if I'm using Excel, I'm just going to go ahead and use the norm dist function. Yeah, so if I have true here, it's a cumulative distribution function. If I have false, then it's the probability density function. So here, when it's true, what's going on is that this gives me that monotonic increasing curve from 0 to 1. If I use this false, that's giving me the bell curve value. So the area under the bell curve is how we get to the cumulative distribution function. Now, if I want to use the quantiles, if I want to take the inverse of the cumulative distribution function, I do norm inverse right here. And the pth percentile of a general normal distribution can also be written in terms of the percentile of a standard normal using this nice formula here. And you'll notice that I could change this up by subtracting mu divided by sigma on both sides, and I'd have z of p is equal to x minus mu divided by sigma. That's not a coincidence. And so here is just, some example of what's going on. All right, so the probability of being less than or equal to 20.5 when the population average is 16 and the standard deviation is 3, the probability of being less than or equal to 20.5 is about 93%. Now, the height of the bell curve, so this curve here is a little bit different, is not what's actually being represented here. The probability of being less than or equal to 11.5 when we have population average of 16 and variance of 3 is about 7%. If I want the probability of being between 20.5 and 11.5, I just do subtraction to get about 87%. All right, so linear combinations of random variables. If I can represent a variable as a sum and difference of other random variables, then I can usually use the normal distribution. So sum and differences are more complicated linear functions of random variables. So multiple random variables are being used, and these come up a lot. A linear combination L of the random variable of my x's is defined as any function where I have a coefficient times random variable, coefficient times random variable, coefficient times random variable, and then I add those up. That's called a linear combination, or possibly a contrast, depending on the values of the coefficients. To compute the expected value and variance of the linear combination of random variables, we use principles that the expected value of the sum of n random variables is the sum of the n respective random variables. So the random variable, or the expected value of the sum, is the sum of the expected values. And that is what's being represented in here. And now, if all the random variables are independent, then it works out that figuring out the variance is relatively easy. So the variance of the linear combination is equal to the sum of the variance of the random variables times their coefficients squared. All right, if my x's are independent normal random variables with expected values of all of these mu's and all of these different variances, so each random variable has its own mu and its own sigma, then it's going to work out that the linear combination that I get here for any constants is going to be normally distributed. And the expected value is just the sum of the expected value. So there's missing an E here. There should be an E with that X. And the variances, as long as we have independence, is going to be the sum of the variances times their coefficients squared. Now, what's going on is that I have multiple random variables. All of them are normal and all of them are independent of each other. If that is the case, then I immediately, automatically know the exact probability distribution, not an approximation, but exactly it. Everything I talked about previously about, sums and averages of random variables, that ends up most of the time just being an approximately normal distribution. Here, why this is important is that it is exactly the normal distribution every single time. All right, dependent random variables. The covariance between two random variables, x and y, is denoted as the covariance between x and y. All right, covariance is similar to correlation, but not quite. There is a difference. When we're doing actual math and doing statistics, with real life data, correlation is easier to interpret. Now, if I'm doing pencil and paper theoretical work, covariance frequently takes the same role as correlation, but in the pencil and paper theoretical math work, covariance is easier. And so covariance can be written as the expected value of the product of the two random variables minus the product of the expected values. Now, if x and y are independent, then the covariance between them is automatically going to be equal to 0. Now, covariance of 0 does not mean that they're independent, but being independent means the covariance is equal to 0. So the way to think about covariance is to think of it in terms of correlation. It's not quite the same measurement. Correlation is covariance rescaled to be between -1 and 1. When we say positive covariance, we mean as 1 goes up, if x goes up, then we expect y to go up on average. If y goes up, then we expect x to go up on average. And if there's a negative covariance, if x goes up, we expect on average for y to go down. If y goes down with negative covariance, then we expect x on average to go up. To obtain a measure of the relative relatedness or association between two random variables, x and y, we consider the correlation coefficient, which is the covariance rescaled by the standard deviations. So this is dimensionless. And so why this is nice is because it doesn't matter what unit my data is in, correlation is always between -1 and 1. Doesn't matter if I'm dealing with feet or pounds or slugs or counts, anything like that. Correlation is always between -1 and 1. So it's easier for us to interpret as humans. So x and y are approximately linearly related. If they're approximately linearly related, a correlation coefficient of 0 implies independence. A correlation close to 1 implies nearly perfect positive dependence, with the large values of x corresponding to larger values of y, smaller values of x corresponding to smaller values of y. Correlation close to -1 implies near perfect negative dependence. So larger values of X correspond to smaller values of Y and vice versa. So here, this is strong positive correlation. You can see that it looks like a line going uphill from left to right. Strong negative correlation, you can see it's going downhill, approximately a line. Here we have a weak negative correlation. Here we have a weak positive correlation. You can see it looks more like a cloud than a straight line. All right, so we can compute the variance of a linear contrast involving two dependent random variables. So here we use that equation that we've talked about previously, except on this point, we're not assuming that we have independence. Previously, when I talked about the sum of a linear combination of random variables, and we talked about the variance, I made the assumption that they're independent of each other. Here, we don't assume that there's independence. And you'll notice that I get the additional term involving the correlation times the standard deviation or the covariance, depending on how you want to write it. So the covariance is usually how we write this, because usually we tackle this type of problem in a theoretical setting, and covariance is easy to work with in that. And so here is a more general presentation of the variance of a linear combination. And you can see that it's, got a lot of summations going on in there. If X are all normal random variables with expected values of the mu's and variances of sigmas squared, and L is any linear contrast linear combination, then L is normally distributed with expected value of the linear combination of the expected values. And the variance is this formula here. So if I have independence between all of the normal random variables, this is equal to 0. And we just have the sum of the variances times the coefficient squared. When I don't have independence, I have this covariance correlation aspect coming into play. Right, the normal approximation of the binomial distribution. Okay, so in the binomial distribution, I have n trials, and my number is the sum of the successes. Okay, so what we can do is I can think of that as I have a sum of random variables. It works out when I have a sum of random variables, approximately the distribution will be close to a bell curve, a normal distribution. And so in situations where it's hard to do the computations of the actual binomial distribution, I can go and convert over to a normal distribution that does a good approximation, do the calculations I need, go back to the problem I'm interested in. So for this, n needs to be of a moderately large size, and p needs to be either close to 0 or 1. Then the binomial distribution will be very positive or very negatively skewed. Now, if n is moderately large and p is not too extreme, then the binomial distribution tends to be symmetric and is well approximated by the normal distribution. So if it's closer to p, we get a better approximate, or if the p is closer to a half and n is large, then we get a better approximation with the normal distribution. So here we can see like this curve looks a lot like the normal curve. It's not the normal curve, but it looks close to it. These here, these three, are not close to the normal distribution. So if I was to use the bell curve to approximate probabilities for these three distributions, it's going to be a worse approximation. If X is a binomial random variable with parameters n and p, then the probability that X is between A and B is approximated by the area under the normal curve, where I have the normal curve's population average be NP and the variance be N times P times Q, This is the expected value of the binomial distribution. This is the variance of the binomial distribution. And then I go A minus a half, B plus a half. All right, so I want the probability that a count random variable is between A and B. A and B are two count numbers. It works out that because of that continuous aspect of the normal distribution, I have to do a little bit of a correction. I need to go just a little bit wider, and I'm going to go A minus a half, B plus a half to get the right values. For the special case of A equals B, the binomial probability of X equals A is approximated by the area under the curve bounded by A minus a half, A plus a half. Exception to this is that the probability that our binomial random variable is equal to 0 or n, the minimum and maximum values, these are approximated by the area under the curve to the left of a half and to the right of n minus 1/2, respectively. So these two are so extreme out that we have a special rule for them in our approximation. Now, something that we're going to talk about a lot is the central limit theorem. The central limit theorem is that idea that I referred to earlier, that if I have a linear combination of random variables, or I have an average of random variables, then we're going to have approximately the normal distribution in some way, some shape, some form. So the larger the n, the better the approximation in general. The reason why this is important is that this gives me a way of understanding complicated random variables without having to do a whole heck of a lot of work. Let X be a random variable that takes on the value 1 with probability P and the value of 0 with probability 1 minus P. This is called Bernoulli. It's a special case of the binomial distribution. This is called a Bernoulli trial. So this is a binomial random variable with one event, one chance. What we do to invoke the central limit theorem is I treat my binomial random variable as the sum of Bernoulli random variables. If I'm taking the sum of Bernoulli random variables, I'm taking the sum of random variables. Therefore, I can invoke central limit theorem. All right, so the normal distribution with mean NP and variance NPQ can be used to approximate the binomial distribution, with, n events and P probability of success when n times P times Q is greater than or equal to 5. Basically, the bigger this is, the better of an approximation we're going to get. And here are some plots. And so here, when we see that n times P times Q is larger, we'll have a better approximation than when n times P times Q is smaller. So here, the P is the same every single time. So the n times P times Q, the P times Q is the same. The n is getting bigger. The bigger the n, the better the approximation with the normal distribution. The normal approximation to the binomial distribution works well whenever n times P times Q is greater than or equal to 5, which corresponds to n moderate and P not too large or too small, are generally not the same as the conditions for which the Poisson approximation to the binomial distribution works well. And so different situations, we're going to use Poisson distribution. Different situations, we'll use normal. Poisson distribution is big N, small p. The normal distribution can also be used to approximate discrete distributions other than the binomial, particularly the Poisson distribution, which is cumbersome to use for large values of mu. A Poisson distribution with parameter mu is approximated by a normal distribution with mean and variance both equal to mu. And once again, we have to do that plus and minus a half to compensate for the fact that we're approximating a discrete random variable with a continuous random variable. And so here we can just see that with a Poisson distribution, with a larger mean, we get a better approximation with the bell curve. Here, this does not look like a bell curve. Here, it looks more like one. All right, so that is all I've got for you. Take care and goodbye.